Well, I'm very grateful for the opportunity from the Simons Foundation for all of us to have this wonderful collaboration, and working on that closely with Roger has been obviously extremely enlightening for development of my career. So this is a picture from our renewal proposal, and it kind of summarizes our main achievements on the neutron star end. And how I'm going to structure this talk is that I'm going to guide you through this new organization, which we came up for two reasons. One of them is that most of our members have most interest in understanding physical processes. And the second of them is that there is a majority overlap of importance of all of these processes to both neutron stars and black holes. So that's why we did this little restructuring, which also hopefully will help you understanding of where we are going forward. So we have these four themes: radiative processes, magnetized flows, extreme magnetic fields, and particle acceleration. I'm going to start with radiative processes. So radiative processes is obviously a very wide topic. And obviously, we're not going to rediscover what's written in Rubicki and Lightman. And most of this is concerned with generation of coherent emission, but also to understanding extremes of producing X-ray bursts, accelerating protons in extreme environments that they could produce neutrinos, ultra-high energy photons that have been a big theme of recent few years on the observational landscape. And given the time, I will only go into the coherent emission generation. This obviously concerns fast radio bursts that Amir talked about yesterday, but it also concerns pulsars and magnetars. I think in the future, the exciting topic is going to be the longer period radio transients that have started to be discovered. Some of them are binaries with white dwarfs. Some of them could be long period magnetars. And lots of details about how their coherent emission could be generated are still unclear. So that's something that we're not yet working on, but I envision many of us will work going forward. And to summarize our goals here is that we want to understand the ground rules of the game. How does the plasma behaves in these environments so that it can produce what we see with telescopes on Earth? In terms of characterizing the observables, we are mainly worried about things like luminosity, spectra, polarization. And in some cases, I would worry that we could even start to predict the variability. Obviously, this theme and this field has a bright future. FRB outriggers on CHIME has already started to produce localization of the sources. SCEECS going to discover lots of pulsars in the galaxy, probably most of the visible ones, including many more millisecond pulsars. DSA 2000 is obviously a discovery machine that's going to unravel lots of radio transients. Some of them we maybe did not see or anticipate before, such as FRBs. So I decided to summarize the observational landscape of this enormous field in just two plots. And going back to the start of Roger's talk, where we were talking about the weather, I like to think about this plot as seasons on neutron stars, and this plot as a daily weather on neutron stars. And what I would argue is that the advancements in simulations and in theory of plasmas of these objects over 5 years or so should be able to explain at least part of this seasonal diagram. Meaning, why would the crab being able to produce normal radio emission, giant radio pulses, nanoshots? What would be the typical duration that is given on this axis? Was it the typical power that this burst would have? So all of that summarizes this observed population over more than 15 orders of magnitude in luminosity and 9 orders of magnitude in duration. These things should be governed by some simple, comma quote, extreme plasma physics rules. What's going on in terms of the variability probably has lots of impact of what happens in the particular source. And I like this particular plot because, as Michael Kramer discovered a few years ago, this quasi-periodic variability has a common similarity across the population of sources. It's seen in rotation-powered pulsars, it's seen in extreme magnetars, it's seen in FRBs now. Whether this is a signature of a rotational period, as that paper invokes, I'm not sure. But there is certainly something going on that is common across the sources, at least on the ground physical level perspective. So what makes me feeling that we can actually make progress here? Well, if I look into perspective of this, pulsars have been discovered in mid-60s. It's been 60 years since they've been discovered. And for 50 years, what has been going on in this field is, at most, coming up with some model for linear plasma instability that could operate, calculate the growth rate, decide whether it can be excited or not, and then basically go on to plugging in very uncertain parameters, similar to where the magnetized accretion field has been before the Balbus and Hawley work. What this has been playing with is the alpha parameter that was unconstrained. We did a lot of progress in this field since roughly 2019. What we have now are concrete physical processes that we can simulate with certain restrictions that Amir went into his talk in more details for FRBs. I'm going to summarize some of them for these processes. But there are concrete physical mechanisms that we could work on and try to understand how efficient they are in producing coherent emission. What are the possible signatures that we can explain with observations? So these are examples of these 4 processes. These are pair discharges, the lightnings near the neutron star surface that intermittently produce electron-positron plasma. And as a consequence of that, they're exciting electromagnetic radiation. This is obviously relevant for pulsars. The other processes that is relevant for pulsars, as I would argue, is magnetic reconnection that happens in the wind of the rotation-powered neutron star. It fragments this current sheet into a sequence of magnetic islands that are merging with each other. And as a consequence of that, there are electromagnetic waves that are escaping from this region. So this can be also relevant for fast radio bursts, as Yuri Lyubarsky proposed in 2021. And Amir talked about in great details about the other model that is also investigated with simulations about how highly magnetized shocks, either in the wind from the magnetar, where the explosion is colliding with the wind, or deep in the inner magnetosphere, where the monster shocks are occurring. What happens here is that there is a coherent gyration of all of these particles at the front of the magnetized shock, creating an unstable distribution that rings in electromagnetic waves. And the process that we discovered during this collaboration, collaborating between my group at Maryland and Andrei Beloborodov at Columbia, is that the two-stream instability, the mechanism that has been long suspected to be a source of pulsar radio emission, could be responsible for emission from magnetars. So these 4 processes are investigated in different level of details. Some of them have been investigated with 2-dimensional and 1-dimensional simulations. Some of them are currently investigated with 3-dimensional simulations. And the future program is basically to try to increase the realism of these calculations. 3D is obviously important. We need to do 3D fully kinetic simulations of these processes in order to understand predictions for power, spectrum, and in certain cases, variability. I'll come into this for pulsars at the very end. How do these processes produce emission that is transmitted towards the observer? Amir talked in great details that propagation effects in the magnetosphere or in the inner wind can be tremendously important. We are just starting to understand some of this. Are there any additional emission mechanisms? Well, most certainly there are. It's just the subset of processes that we were able to calculate for now. We have other ideas, but this has not been emerged as a working model so far. An interesting question that we had and do have still when we started this collaboration is whether some of this can be probed with laboratory experiments. And what I think here is that the laboratory experiments are obviously not going to reproduce a fast radio burst in the lab. The A parameter that modern experiments could do is at most 10, not hundreds, or not even hundreds. And the real sources have A of order of 10 to the 5 or so. in their inner magnetosphere. So again, what would happen here is that experiments would provide test beds for testing ideas and physical processes that could operate in real sources. And lots of it lots of this interaction between this community and the community of laser plasma experiments did happen at the KITP program that some of us co-organized in the summer. The question connecting to observations that I want to connect to, and what we will have a debate on after my talk at 2:30, is what are the locations of the emission, where it is produced both in magnetars, pulsars, and FRBs. Pulsars in this case are the most studied objects, obviously, and in that case, I think there is an emergence of a really clear-cut answer from observations, that there is at least two regions where there are different emission mechanisms powering the emission, producing different signatures in what we see in radio telescopes. So I don't think putting all the money on single emission mechanism is wise. It's not supported by data from pulsars, and we need to investigate more possibilities. And what's ultimately important is that could all of this work be used to formulate a robust observational test that we could ultimately use and understand whether some of this are operating or not. And with things like DSA 2000, we must also be prepared for unexpected discoveries, because no one expected pulsars as coherent radio sources. They've been expected as rotating neutron star sources by Pacini, but I don't think he thought about them as coherent emission sources. And FRBs were obviously completely unexpected. So there should be more stuff coming there. OK, moving on. The next topic is magnetized flows. This is concerning mainly accretion onto black holes, the topic of talks by Zvi and Ellen. This encompasses a variety of different environments, starting from little stellar mass black holes and X-ray binaries, to humongous AGN and gamma ray bursts, the most explosive events in the universe. What I will argue is that we should not use our MHD codes just to understand black holes. And if you're a student or postdoc, I deeply encourage you to, if you're using an MHD code, to think about something else rather than the black hole accretion. I think an example of Kushik, who applied his technology to a magnetar explosion, should be seen as the standard, not as the exception. And the other object that I'm excited about in the coming years is actually pulsar nebulae. And why I'm excited about this is because we have now exciting observations with the X-ray polarimeter, XP, that I will discuss in a second. They provide arguably very controversial and very interesting things that we should explain. But also they have been sources of ultra-high energy photons. So they're exciting particle accelerators, and we don't understand much of it. And in my mind, most of it comes from because the simulations of these objects are actually, the most recent simulations are dated to 10 years ago. So they have not been as advanced as the simulations of the accreting black holes by far. So in this case, there is a synergy between multi-scale approaches that we would be undertaking. We're concerned both about the global structure of these flows, as I would argue next, most of this is still uncertain, and also incorporating the necessary microphysics along the way, as Ellen stressed a lot in her talk. There is a bright future in observations here. New generation event horizon telescope, maybe BECS. They would see even better images of the event horizon of M87 and Sagittarius A star. They would produce movies that would test our ideas about erupting magnetic flux from the event horizon. The time domain observations, including new observations with James Webb Telescope, are producing even more details about how the Sagittarius A star is producing flares. And on the high energy end, what I'm most excited about is this mission COSY, or actually any further more sensitive mission in the MEV band, because that's currently completely uncovered. And it is extremely useful to understand, for example, these models of producing particle acceleration in X-ray corona. The models that produces, starting from post-processing MHD simulations, obviously produce purely thermal spectra, while our particle and cell simulations produce a weak tail in the MEV that COSY could see. and that would be used as test beds for diagnosing conditions in this corona. The landscape in the last few years has been quite bright. I don't have to tell you anything about the ring of light from M87. XP has been extremely exciting for both the black hole coronae, observing polarization and suggesting possibly outflows from the coronae, but also seeing tremendous polarization in the pulsar wind nebulae. So what you see here is that this tiny little pulsar, the 10-kilometer wide, produces humongous current flow that extends to light years. And what you see with XP is remarkable polarization, the X-ray polarization reaching 60%. That is really close to the theoretical limit that is possible for synchrotron radiation. So what's obviously happening is that the particles have to be accelerated, hopefully by some turbulent processes, but how they emit is almost insensitive to all of these details. What they see is a radiation by extremely coherent field with very strong polarization. In my mind, this is a very exciting puzzle that hopefully we will be able to work on as a combination of large-scale and small-scale approaches. So the global models have been advancing for black hole accretion. Arguably, after EHT observations, the community moved away from sane solutions, and magnetically arrested disks are now a new standard. I think this is not the end of the game, and why do I think so is because as community is moving away from this more simplified torus-like models, what they see is that the progressively highly and more highly magnetized disks are emerging. So what this simulation by Elisa and also by Aris at Caltech and CETA, and also by Herin Cho recently, who reproduced these results with Ramesh Narayan, starting from, again, more idealized but more magnetized torus simulations, is showing is that as the accretion flow is proceeding, it basically magnetizes itself in a progressively larger volume. And the conjecture that Herin made in her paper, and is what we were approaching, I think, in this paper as well, is that these solutions will magnetize themselves up to a Bondi sphere, basically. So everything within the Bondi radius, if you proceed like that, would be extremely magnetized. Is that the limit? Or maybe we could magnetize themselves even more, as in Rogers and Naomi's model. I think it's an open question, and I would love to understand this better. I would love to understand how the flux is transported and amplified through thin disks. And this is one of the attempts that we made for thick disks. Thin disks are even more complicated, and I think this is a very important area of research. There have been progress in incorporating microphysical effects. This is a result of collaboration between CETA, Columbia, and Maryland, where we are not even using machine learning, no. This is discovered by a pure force of brain power. This is a prescription for collisionless plasma resistivity. So basically, the non-uniform resistivity driven by the charge starvation, the inertia of the particles that I needed to vastly quickly be accelerated inside X points in highly magnetized relativistic reconnection, is setting the resistivity for the plasma at very tiny scales, and that defines how the reconnection can convert magnetic flux into heat on bigger scales. And this has been already incorporated in some of the MHD simulations. This is this prototypical problem of black hole balding, where you start with certain magnetic flux on the black hole and then see it shredded through the large-scale reconnection sheet. This is affected by microphysics. And similarly, the flux eruptions in magnetically arrested disks could be affected by this physics. There has been this another advancement that I was not able to put on the slide because the paper appeared on arXiv just on Wednesday by Yaj's group that advanced our previous developments with ELISA about the fully collisionless accretion simulations, general relativistic particle and cell simulation that Zvi showed in his talk, but now starting with more realistic initial conditions with finite angular momentum, that did show certain features of MHD flows. It also confirmed that the anisotropic pressure stresses are less important than the Maxwell torques. So the highly magnetized disks are mainly determined by the dynamics of the magnetic field, but they also discovered the same eruptions, similarly to the MHD arrested flows. So I'm looking forward to see how reconnection is actually shaping them with more realistic subgrid prescriptions for this physics. So this just summarizes what I just said. The global structure of these flows, I think, still needs more investigations, both in thick and thin flows. Collisionless physics need to be brought in, at least at the level of dynamics of reconnection. That certainly looks like a sizable effect. The transport of magnetic flux from large scale to small scales, and this is going back to Dong's question, asking Ellen. I think to some extent we still need the large-scale field that needs to be attracted from larger scales. But we also show that purely toroidal field disks, for example, could produce efficient Blanford-Znaik jets. So an interesting question arises here: could we actually distinguish, potentially observationally, these possibilities? Is there a coherent jet in most of these cases, like in M87? Or the striped jet that continuously dissipates on a wide range of scales? Polarization and images at the jet wall could provide discriminatory opportunities for these options. What troubles me really is what the geometry of the disk Caroni. And I have to say that before this collaboration started, I really thought the key question is to calculate the microphysics. Well, I can now calculate the microphysics, I think, fairly reliably, but that doesn't tell me anything about what the actual corona is. The stromal peak is surprisingly agnostic to the microphysics properties. What it mainly depends on are the properties of the radiation flow that we are putting as proxies for our small-scale simulations. What we really need is a large-scale understanding of what this region is from the global fluid dynamics simulations, I think. What we did not really cover in these talks, and what, for example, Amir teases me every time we talk, is what about GRBs, GRB jets? That it's another example of a system that is prone to more investigations with MHD codes, and we did not do yet. So how do these flows dissipate, for example, is an extremely exciting question that I think many of us would be moving towards in upcoming years. Okay, this theme 3. Extreme magnetic fields. This comes mainly about talking about neutron stars. Yuri gave a beautiful talk at the very beginning of our meeting. I would not try to go as in depth as him because that's not really my field of expertise. The key questions that they want to answer is basically to bridge connection between the interior and the exterior. And as many of us discussed, what you need to predict the observables from neutron stars are the physics happening in the interior and the exterior. What it definitely is affected by is the physics of what happens inside the neutron star. And that's what this part of the collaboration is heavily working on. So what they want to produce is models of the interior physics that can be used to connect to the exterior, to the predicting how the pulsar glitches are happening, or how do the magnetar outbursts producing fast radio bursts would eventually happen. As I said, there is a bright future for radio observations. There is also this exciting Chinese mission, extreme X-ray timing and polarimetry mission that I will come out at the very end, so you would see why I'm excited about this. The landscape is vast, and Yuri gave a very thorough introduction into this. What I, as a plasma physicist, love a lot about this is when I give a talk about pulsars, observers typically ask me about, oh, what about the breaking index? Or what about this correlated variability between the spin down and the radial light curves? Well, I have no clue. And why do I have no clue is because it happens on timescales exceeding months, or in certain cases, years. My little plasma magnetosphere doesn't know about these timescales. What these members of the team are coming from is basically they're saying, OK, this is probably produced by the interior physics, and let's try to come with models that would explain it. And as you saw, there is extremely exciting work about the giant hallways that could be responsible to this, and the dynamics of vortices that could discover physics for pulsar glitches. And we talked a lot about the gamma ray flares from magnetars. I don't have to tell more you about this. This is the landscape of progress that has been done here, and this is the work that's been highly collaborative between Columbia group, and also a group at Illinois State by Matt Kaplan. This is an example how two causally disconnected different fields are coming together. Matt Kaplan is bringing his molecular dynamics simulations. In this example, they have been heavily refactored into including magnetic fields and into seeing how the magnetized crust can actually produce magnetized folds. And in this case, they studied how the giant Hall waves at the boundary between the core and the crust, due to the superconducting phase transition, is creating waves that can eventually emerge to the stellar surface and affect the physics in the exterior. This is an example where you could see how the collaboration between people working on the interior physics and then on the magnetospheric physics is emerging. What basically happened here is that Ashley Bransgrove came to Maryland, and over a few days, Kushek put the results of his interior physics simulations as the initial conditions for his giant flare eruptions. And now this would be advanced more, meaning that we could go all the way from the dynamics of ambipolar diffusion inside the neutron star, evolving the magnetic field in this object, such as there's giant magnetized eruption would be produced from the stellar surface, and then the exterior MHD code would pick from this and evolve it through expansion of this blob to infinity, producing the outflow that could be used as driver of fast radio bursts, but also as a mechanism to produce giant flares in the tail of the current sheet and as a fireball of dense matter trapping radiation close to the surface. So that's an example of a benefit of having all of this expertise in the collaboration. We can go really from interior physics to exterior physics and hopefully for predictions to observations. The future program, I don't have to repeat it probably. This is determined by needs to explain this long-term variability seen in pulsars and bursts of magnetars. Yuri talked a lot about this. What I will do, a simple connection here, is that some of us has been interested to how to connect this magnetospheric models to produce better models for explaining, not explaining, well, to highlighting possible features of axions that can either be produced near neutron star surfaces or being converted into observable photons near the surface. Ani Prabhu, the postdoc at Princeton, has been really instrumental in bringing this communities together. So now it's routine that in the community of people writing papers about axion physics around neutron stars, they're actually using very realistic models inspired by plasma physical simulations to make certain predictions about this. So obviously, this is a long shot. We don't know whether they exist or whether they are plausible dark matter candidates, but we are definitely facilitating the exchange between the two communities for this. So I'm coming to my last topic, particle acceleration. This has been covered in large details in a very comprehensive talk by Anatoly. What we're excited here is that the microphysics is, in some aspects, is again reaching certain level that we could try to connect these advancements to predict the multi-messenger observables. And I'll give a list of sources that, for example, I'm most excited about for making these connections. The obvious challenge is also to explain the acceleration to the ultra-high energies that Roger and Naomi wrote papers about, but some of us are also thinking heavily on. There have been a lot of progress on the observational landscape by Lasso and Future, also Hess and Veritas, and the Cherenkov telescope array coming online, hopefully in a few years. We'll discover way more of these sources. We need to be ready for connecting our models to large-scale systems in these cases. And this doesn't really go all the way to highest energies. The problems start already at low energies. This is a famous example of the jet wall in Centaurus A by EHT, and there are many more examples like this. The jets are bright at their edges. The Lorentz factors of electrons producing this light is relatively tiny by standards of all other systems. You just need Lorentz factors of order of 1,000 close to the black hole to produce these images. What's interestingly puzzling, and that's what has been proposed in a paper by Ramesh Narayan's group, is that this emission, to produce the significant limb brightening of the jet, you may have to take into account of the particle anisotropy with respect to the magnetic field. And that's actually what the models of particle acceleration and turbulence and in reconnection are naturally predicting. The lowest energy particles, they feel this strong field, the guide field inside the turbulence or in the reconnection layer that is guiding them to accelerate along that direction. So that's a natural way to produce highly anisotropic distributions at low energies. Whether this effect could explain the limb brightening all the way close to the black hole to a much larger scale, where you would need larger and larger energy particles, is currently a mystery. And I think this what we will be heavily exploring in this collaboration. How do the results of our microphysical calculations could be mapped on this much bigger scale systems? And at highest energies, there are many more challenges. What is particularly exciting, I think, is the discovery of many microquasars, the SS433, and recently also Cygnus X3, as sources of ultra-high energy photons, I think in this case exceeding 100 TeV or so. This happens at much larger scales compared to where the central black hole is, and the obvious candidates in this cases are shocks. We've heard a lot from Anatoly about how the simulations are advancing to much bigger scales to incorporate the feedback of accelerated particles in the process of particle acceleration. I think this is a natural target to test some of these models eventually. And obviously, the ultra-high energy cosmic rays, as the telescope array and Auger are discovering new and more particles, we should start asking the question of, is there even a possibility to discover sources of this, or is this completely hopeless? The progress on particle acceleration front, I like to systematize in these three different avenues. First is that we are now self-consistently putting radiation into our particle and cell acceleration models. Even, say, 5 years ago, we've been mainly talking about purely radiation reaction effect on the accelerated particles, limiting the highest energy that leptons could reach in the systems. What we are talking now is fully integrated modules for Compton scattering the distribution of photons self-consistently on accelerated leptons, in some cases also incorporating pair production. And as more and more physics comes in, hopefully we would be able to come to the point where predictions of the simulations could be meaningfully compared with some observations. This is an example that Anatoly also showed. This is an example of a simulation of magnetized turbulence in a densely radiative environment that is expected near the highly accreting black holes. And what it shows is that you can not only produce a thermal electron background, but also the tail of the electron distribution that could produce MEV tail, for example, that COSY would see. But what they also show is that these environments are natural accelerators of protons. In this case, we found a fairly steep power law for protons, but we are also looking into other possibilities that could enhance this acceleration. And that would be possible, then these systems would be natural candidates, at least, as neutrino sources, because these accelerated protons could collide with X-rays and through P-gamma interaction be great sources of neutrinos. I think this is an exciting direction going forward. We're uncovering fundamentally three-dimensional role in acceleration mechanisms that were not possible to address before. And this is the same example from particle acceleration and reconnection, that by removing the restricting assumptions of two-dimensionality, we are able to efficiently accelerate particles, which was not previously possible in 2 dimensions. And again, as Anatoly said, we are coming to models where we can incorporate the feedback of high-energy particles back into the simulations meaningfully to describe the multi-scale feedback in the systems. I think this is very important in order to bridge scales and go back to be connected with observations. So the key questions going forward, I think, is that we will be working on is to extending the simulations where the full role of radiation and quantum electrodynamical feedback is incorporated into these plasma simulations. What I showed you, just one example of the environment where this physics can be important. There is way more of this sources and classes of objects that we could investigate. We are moving on to putting this mechanisms of particle acceleration into broader models of astrophysical objects, hoping to make connections with observations. And what's not only important is how particles are accelerated, but also how are they transported and confined. And this is exemplified by observations of TeV halos about pulsars that Ke-Fang at Madison has been greatly involved in. Also by what Andrew Sullivan and his colleagues at Stanford are working about the filaments threading from pulsar wind nebulae. Obviously, accelerated electrons need to be meaningfully confined there, and this connects back to issues of cosmic ray transport in a galaxy and otherwise. Again, what we are hoping to bring together is understanding of particle acceleration and transport of these particles through turbulence and self-excited instabilities, hopefully to make connections to observed systems. This progress has been going forward together with advances in numerical methods. We heard already a lot about advances in numerical methods affecting the modeling of neutron star interiors. This is, again, incorporation of magnetic fields into molecular dynamics simulation, also coupling the molecular dynamics simulations of the lattice with simulation of single superfluid vortices and how they propagate. I would not go back to that. What I would describe is mainly two specific advancements in particle and cell and other kinetic methods of simulations. This work has been possible also in collaboration with plasma physics lab at Princeton due to generous support of Bill Dorland and Steve Cowley. This code started when Heike Kabyan was working at PPL entity. What it basically does now, it incorporates all of this physics that has been previously jointly disconnected in 4 or 5 different codes, is now brought all together into a modern code that is capable of running on GPUs. It includes radiation physics and general relativity, supporting various types of computational grids. And to give you an example of where this is going is that this is the largest plasma physical magnetized turbulence simulation that was performed basically as a test run on Department of Energy's Frontier cluster, just in order to be able to apply to their machine. And this what tells you what is the future. The future is that this things running at 10,000 cube would be pretty much routine, I think. This is the famous, well, already famous, reproduction of Parfit et al. Of 2019, which back 6 years ago took us quite a while to calculate. Now this thing works on at 2 hours on just 8 GPUs. And if I remember right, this is a factor of few higher resolution. So these models are becoming much more easy to compute, and that allows them to incorporate more physics. What Heike is also heavily working on is building community about this code. So there is a Slack channel that users of the code are jointly involved with. He hosts a telecon once a week, every Monday. I think it was going literally every Monday for a year now without losing a single Monday. Everyone in collaboration is hoping to also be involved. And I also encourage people outside of our collaboration to start using this code, because it also helps us in a sense that we'll discover more features and ways to optimize usage of all of these things. This is something I'm particularly excited about, and I did hope to show you a simulation on this for this meeting. This is something that we did not complete yet. In future, I think we'll be doing 3-dimensional simulations of this on this grid called Cube Sphere, which connects 6 patches on the sphere causally disconnected without having the access problem and time step issues. And we're almost there, actually. Hopefully next year I'll show you a simulation running on this thing as a poster. This is another example coming from the same collaboration with the Plasma Physics Lab. what we have all been doing before, we've been simulating this plasma physical systems using particle and cell codes. They have great advantages, and many discoveries were made using these codes. There is an alternative, and that has been used in the space physics community for quite a while, and also in laboratory plasma physics, is to use a continuum model. What I mean by a continuum model is solving the straightforward Vlasov equation directly on the grid as the partial differential equation. Obviously, you can ask, am I crazy? This is a six-dimensional problem. How am I going to put this on a computer? Well, in relativistic systems, in highly magnetized systems in particular, there is a great advantage. If I put my plasma particles next to a neutron star, in 10 to the minus 13 seconds, they will forget about all the perpendicular motion. So the plasma motion is intrinsically one-dimensional, close to the neutron star. And that's where the advantage and power of this continuum codes really shine. These are three examples of projects going on now. We're applying these codes to pair discharges. And why I'm excited about this connects back to this question about weather on a neutron star. The weather on the neutron star is set by this variability of radio emission that is flickering on microsecond timescales. And what I think this is connected with is with intermittency of producing electron-positron plasma. So plasma is produced for a certain time, it screens the electric field, nothing happens for some time. And then obviously there will be no radio emission. And what these models are showing is that this time scale of repetition of these different plasma production events is too short. It's by a factor of 20 times shorter than what we see in the variability of neutron stars. And it also connects well to the other issue by connecting this to thermal X-rays that I will come in a second. That may even be important for measuring the mass radius from neutron stars. So understanding this little simple piece of physics of how frequent these things happen may have implications for both understanding the equation of state of a neutron star and variability of radio emission from the sources. Where the physics is coming in? Well, you need to send a 1% of particles back to the neutron star from this dense cloud of electrons and positrons in order to affect the electric field at the star. So this is a highly nonlinear process. You need to accurately understand how the particle trapping in electrostatic turbulence is happening in order to predict the flux of particles going back to the star and affecting this. This is where I think the continuum models will shine. This is another example that I think Dong asked about, or it emerged in that conversation about what would happen when the beam of accelerated particles in the magnetosphere of a magnetar is colliding with the atmosphere. Well, it will excite electrostatic turbulence, and that can also be simulated with these methods. Maybe the infrared emission from magnetars is a coherent infrared emission from magnetars is happening right here on the surface. And that's the same example of a two-stream instability that arguably has only been possible with the continuum code because we ran the peak simulations. It was not converging even when we ran up to a few thousands of particles per cell, and we desperately needed a proof that what we see at late times is actually the right choice. And the continuum method has been really instrumental in doing so. OK, so Roger and I talked about that we need to not only describe what the collaboration is doing, but also come up with certain things that we are particularly excited about. And in this example, I will try to guide you how all of these different disconnected plasma physical advances may actually affect broader scale physics. So this is a famous example produced by NICER collaboration that used thermal X-ray light curves of pulsating millisecond pulsars to constrain the mass and radius of neutron stars. How do they do it? Is because the light curves are sensitive both to both general relativity, the ratio of mass and radius for compactness, but also for Doppler boost, because the star is highly spinning, so the light that you receive is affected by the rotational velocity on the surface of a neutron star. So in that case, you can break the degeneracy. It's not only the observation is sensitive to the ratio of mass and radius, but also to the radius itself. What you don't know in these models is where these hotspots, the bright spots of, on the surface of a neutron star that are emitting this X-ray light are actually located. What this groundbreaking work has been doing until now, they have been putting assumptions and basically defining by hand where the emission is coming from, drawing little circles and arches and calculating light curves and in 12-dimensional parameter space, trying to optimize for shapes of the surfaces and also mass and radius. Not surprisingly, the error bars coming from this modeling are quite large, both for radius and mass. So what I want to go is to understand physics of these hotspots. And there is actually a lot of physics going on here. So where do these hotspots are coming from? Well, they're coming because we have this QED lightning on the surface of a neutron star. Some of the particles come back to the star naturally. They heat these regions, and the heated atmosphere is emitting the light. Well, what would you find? Well, typically we find that the models that we are coming with, both the large-scale magnetospheric models and the small-scale models of paraproduction discharges, they're producing spots that are 10 times bigger by area. So this spot is 10 times smaller than what any of our models would produce. So is this a shortage of our magnetospheric models, or should they put different priors about how big their hotspots are? Well, I'm obviously thinking that the geometry of this magnetosphere is very well constrained, so the hotspots have to be this size, not this size. What we can also predict is that the temperature of these hotspots have to be non-uniform, so you can confuse a bigger spot with highly non-uniform temperature with a single spot. What they're also doing is that with this process of reconstructing shapes of this hotspot, sometimes the MCMC chain is producing a non-unique answer. In some cases, you can produce these little red dots, bright little dots in the centers of polar caps, completely not sensible from the point of view of giant scale electrodynamics. So how we could disentangle all of these possibilities? Well, in fact, we have lots of other multi-wavelengths data. We have radio polarization, we have gamma ray light curves that are also providing independent proofs for how the geometry of the magnetosphere is looking like. So this is where all of 4 SCEECS themes could come together. We can use enhanced understanding of radio polarization and the radio emission produced in theme 1, combined with global scale models of these objects, the global magnetospheres from effectively theme 3, coupled with subgrid models that would tell us how the acceleration of particles in these current sheets is happening and the emission is produced without simulating the global scale peak simulation every time. And that could be mapped into large-scale gamma ray light curves that could be compared and helped nicer analysis to infer the obliquity and the geometry of the magnetosphere, because this is what this gamma ray sky map is most sensitive to. So all of this cleaning plasma physical garbage, as you would like to say, eventually could help understanding deep mysteries about the equation of state of a neutron star. Whether it will actually work out, or maybe the degeneracies in the parameter space will still be very huge, I don't know. But obviously, I'm very excited about this. And also because this Chinese mission would produce much more quality data by 2030, right at the end of our renewal. So hopefully, we'll be able to clear out all the systematics, or at least some of the systematics in these measurements, and just be limited by instrumental systematics of this mission, not by lack of understanding of X-ray hotspots or gamma ray light curves. So this is to close. These are the 4 topics that we expect to be pursuing in the renewal. As Roger said, it's very hard to put these people inside boxes. I try to do so. So we have people who are mainly working on one topic or the other. And we have people who cannot be put into a single box by whatever metric. So they would be connecting the magnetized flows and particle acceleration, for example, or extreme magnetic fields in the interior with the radiative processes on the outside. So I hope I convinced you that we have an interesting future and lots of work to do. And I'm happy to take questions.